as Tadashi did by thanking the organizers for inviting me, and also by thanking the audience for showing up at the first session of the day after yesterday's very late evening. As many of the other speakers have said, but it's also true for me, it really is such a great honor to be here and a pleasure to congratulate Spente. I first got to know him when I spent a year as a postdoc at TIFR, which was one of the most fun years of my life, both personally and scientifically. And so much of that was thanks to the incredible hospitality and warmth that Spente showed to me. And I think I can deputize myself to speak on behalf of all of the foreign postdocs who were at TIFR around that time. He just did an incredible job making us feel at home and making our lives as smooth as possible. And a lot of what he did to do that, I think we weren't even really aware of at the time. And a lot has been said about Spente's scientific and institution building accomplishments. And I think this was mentioned briefly last night, but I do want to mention one's perhaps slightly more obscure accomplishment, which is that the archive was Spente's idea. I want to highlight it because I think it was David Merman who very generously explained that the archive is probably string theory's greatest contribution to science. So taking that into account, it just reconfirms, of course, what we already know, that Spente is one of the greatest string theorists. Okay, so today I'm going to be talking about the large N limit, which is Spente's favorite limit and mine too. And specifically, I'm going to be talking about that in the context of holographic dualities, which are now in their modern form 20 years old. In my opinion, one of the most important developments during those 20 years, about halfway through, was the discovery of holographic entanglement entropy. And I think a lot of people believe, as I do, that the holographic entanglement entropy formula that Tadashi and Shinsei Ryu gave us contains some information about the nature of the emergence of space-time. But somehow we haven't quite figured out yet how to decode that information. And so what I'm going to say in this talk is an attempt to go in that direction. And what I'm going to do is first describe what I think are some sort of conceptual obstacles to understanding the meaning of the Ryu-Takayanagi formula. And then I'm going to claim some progress in solving those conceptual obstacles by taking a new point of view on the formula. And I'm going to explain what the implications are and why I think it's helpful. And then if there's time, which there probably won't be, I'll describe some extensions. Okay, but I want to start with a precursor to Ryu-Takayanagi, which is Bekenstein-Hawking, which is a special case. This is a very old formula that tells us that the entropy of a black hole, and in fact it can be generalized to any kind of horizon, is proportional to the area of the horizon with proportionality constant of 4 Planck areas. And it's such a simple formula, it demands an explanation. Of course, this is a problem we've been chasing since the formula was first written down. But when you look at the formula, of course, the answer is quite obvious. The reason the entropy is proportional to the area must be that the bits that specify the microstate of the black hole must be sprinkled on the horizon of the black hole at a density of 1 bit per Planck for 4 Planck areas. And in fact, if you Google Bekenstein-Hawking and do a Google image search, as I did, you'll get a lot of pictures that look like this with 1s and 0s on the event horizon of a black hole. Of course, we can immediately start jumping on this sort of naive answer. And that's what I want to do. And the way I want to attack it is by bringing up the Ryu-Takayanagi formula, which, as I said, is a vast generalization of Bekenstein-Hawking, and it's a vast generalization because it's a function now. We have an argument A, which is the region on the boundary of the holographic theory, which we're free to choose. And so as we choose it differently, the minimal surface moves around. So let me back up and just say that here I'm working, of course, in the large N limit, in a theory that has a classical Einstein dual. And until the end of the talk, I'm not going to be discussing time. I'm going to be assuming we're in a static state, so we can use the original Ryu-Takayanagi formula, where it's a minimal area surface, which I'll call M of A. That's the bulk minimal surface homologous to A. But the point here is that now it's a function of something, and by playing with that thing, that choice of A, we move around the minimal surface. And that actually causes this answer to kind of fall on its face. So let me explain why that is. Well, I'll give a few arguments. So the first one is that something kind of funny happens as you move the region around. As you change it continuously, the minimal surface may jump. And so in particular, so here's a classic example where you have two separated regions on the boundary, and as a function of their separation, the minimal surface jumps from being one which is the union of their respective individual minimal surfaces to one which joins them. And so you could ask, like, at the transition point, okay, where are the bits? Are they, if we believe this answer that the microstate bits specifying the state of A live on the minimal surface at a density of 1 per 4 Planck areas, then, you know, at the transition point, where are they? Are they here or are they here? Sort of related to that, maybe sort of the same argument, but at a more sophisticated level, is the following issue. There are many important information-theoretic quantities which are linear combinations of entropies. To compute them using Ryu-Takayanagi, you simply compute the individual entropies and then add or subtract them according to the formula. And of course, these the surfaces that you're using to compute these different quantities on the right-hand sides of, let's say, the conditional entropy, mutual information, and so on, those surfaces, the respective surfaces used to compute these things, are passing through totally different parts of the space-time. Let's just quickly recall why it is that we are interested in these quantities, what they mean information theoretically. So let me just start with two systems, A and B, and we have our conditional entropy, we have our mutual information. And the classical case is very simple. There's a compressed coding of the AB state, which essentially consists of 3 types of bits. So these are my bits of A, these are my bits of B, and I've coded it in such a way that some number of bits are perfectly correlated between them. Some number of bits are unique to A and some number of bits are unique to B. And you can see that the number of bits unique to A is precisely this conditional entropy, and the number of bits that are redundant between A and B is precisely the mutual information. And that's why we care about these particular linear combinations. Now, in the quantum case, of course, it's much more complicated. I don't have time to give any kind of complete review. One of the new features is that now, of course, you have entanglement, and where you have an entangled, or maximally entangled pair of qubits, it will be pure in the joint system, and therefore contribute 0 to S of AB, and therefore contribute 2 to the mutual information, and -1 to the conditional entropy, so you can get a negative conditional entropy. And similarly with the conditional mutual information, which is just a souped up version, that's the amount of correlation between A and B. In other words, the number of bits shared between A and B conditioned on C, conditioned on knowing the state of C. Okay, so that's all sort of clear enough. And now we go to Ryu-Takayanagi, we go to the holographic case, and we've got these minimal surfaces passing through different parts of the space-time, and now we're instructed to subtract the area of this from the area of that. And that's supposed to tell us the number of bits unique to A, the number of bits that are shared and stuff. If the bits are really living on the minimal surfaces, then why are we comparing the areas of minimal surfaces passing through different parts? Okay, that's the basic objection. It's something that sort of confused me for a long time. And then, yeah. So the third example or objection, which again is just very closely related to this, has to do with this proof that Tadashi and I gave that the entropy formula obeys strong subadditivity. I'm not going to go through the proof. Many of you have probably seen it, but the upshot is that you sort of do some cutting and gluing of minimal surfaces, again, passing through different parts of the space. And even though, I mean, the proof, it's very simple, it's nice in some ways, but I've never understood what on earth it had to do with strong subadditivity. Strong subadditivity is a statement that correlations as measured by the mutual information are monotonic. In other words, A is at least as correlated with BC as it is with C. This is a crucial statement for the interpretation of the mutual information to reflect the amount of correlation. And so it's a simple statement. The proof is simple, but the connection between them I never understood. It just seemed like almost an accident, like a lucky accident, that Headrick-Takayanagi obeyed this crucial property. Okay, so what I'm going to do to try to resolve these issues is basically just advocate just a small shift in perspective. Just look at the same formula from a slightly different angle. And to do that, I'm going to rewrite the formula in a way that where there's no minimal surfaces. Okay, so the minimal surfaces will be demoted to a calculational device, and I think this new way suggests this new way of writing the formula also suggests a new way to think about the holographic principle and perhaps the connection between space-time geometry and information. Okay, so the rewriting is, as I said, very simple. It refers to a theorem from differential geometry, which is called max flow min cut, which actually originally is from network theory. So a flow, so we have some Riemannian manifold with boundary. A flow is a vector field that's divergenceless and whose norm is everywhere less than or equal to 1. And you can think of a flow by virtue of being divergenceless as a set of oriented threads, which are the flow lines that can't begin and end anywhere in the bulk, just on the boundary. And this condition, so the norm of V, if you think of the like electric field lines or magnetic field lines, their transverse density is the magnitude of the field, so that's bounded by 1. And now if we have some subset of the boundary, so in this cartoon, the subset is an entire connected component of the boundary, but that's just for sort of pedagogical purposes to introduce the theorem. And we have some flow, and we're trying to, so the theorem says that the maximum flux out of A, subject to these conditions, is equal to the area of the minimal surface that's homologous to A. Okay? So that's the theorem. It's one of these theorems, the substantive part of the theorem is, or what I would regard as the substantive part is sort of easy to prove and kind of elegant, and then there's the annoying part about proving minimal surfaces, which is incredibly difficult. I would never know how to actually rigorously prove things about minimal surfaces. Basically, one way to think of the statement is that any surface which is homologous to A, by virtue of these conditions, provides a limit, a maximum on the flux through A, and the strongest bound, the strongest upper bound is the minimal area surface, and the statement of the theorem is that that's the only obstruction. There's no other obstruction to increasing the flux, okay? Now, I want to make a couple of notes. The minimal surface is generically unique, but the max flow is highly non-unique. It's equal to the unit normal on the minimal surface. That's the only way you're going to saturate this. But away from the minimal surface, the flow lines are very floppy. They have lots of room to move around. And I'm going to use this notation where V of A means any max flow for A. Okay? And the rest of the talk is going to be about conceptual implications, but I do want to point out that in various fields of computational geometry, they use max flow min cut as a very efficient numerical algorithm for finding minimal surfaces. And the reason basically is that finding the left-hand side is a convex optimization problem whereas the right-hand side is some nonlinear, non-convex problem with local minima and stuff like that. So this may actually have some practical use. Okay, so let's apply this to Ryu-Takayanagi. We have our new version, which says that so now I'm working in units where the 4 times the Planck area is 1. The maximum flux is going to tell us our entanglement entropy, and in terms of threads, it's the maximum number of threads starting on A going into the bulk. And the threads can end on A complement, or they can end on the horizon. So somehow, as you keep trying to add threads, leaving A, at some point, you can't add any more. So basically, this norm bound on V is saying that each thread has a thickness of 4 Planck areas, okay? And they can't be packed more densely than 1 per 4 Planck areas, okay? And you're supposed to think of each thread as representing 1 independent bit of the microstate of A, okay? And we're going to go through this in some more detail. I want to just point out a couple of properties immediately. This formulation automatically incorporates the homology condition and the fact that you're doing a global minimization. So you don't have to put those in by hand here. Again, the threads are very floppy. So there's a huge gauge freedom. And in particular, you can move around where they attach to A. So it's not that each bit is associated with 1 location in A. And there's also, because there's so much room out near the boundary of ADS, there's tons of room to add threads that start and end on A. Those don't count towards S of A. It's only the net number leaving A that contributes to the flux and therefore to S of A. And what I'm going to argue is that these gauge freedoms are actually very physically meaningful, okay? As gauge freedoms often are, they carry a lot of physical information. Okay, where is the minimal surface? It's just wherever the bottleneck happened to be, okay? And it's a convenient place calculationally because it's the only place where the number of threads is equal to the area, because it's the place where the threads are maximally packed together. So it sort of is a calculational tool. This formulation sort of naturally implements the holographic principle in a very simple way. The holographic principle says that entropies, the maximum entropy you can have in a region of space is counted by the area, not the volume. You might have thought it was the volume because if the bits are sort of stored at point-like objects, then it would be the volume. And this is saying, well, they're not point-like objects, they're one-dimensional objects, therefore you get an area. A unique minimal surface? Yeah, so imagine that they're only floppy away from the minimal surface. At the minimal surface is the bottleneck. It's the obstruction to adding 1 more thread. And at the minimal surface, the threads are maximally packed together, okay? And they're just jammed in there, okay? But away, so the number is bounded by that area. Away, there's all this room and they can move around, but you can't add 1 more. Well, in some sense, so it may be the case that calculationally you could find the minimal surface first, but you can actually implement, as I was saying before, in numerical algorithms, they actually do what I was saying. They keep adding threads. There's a way to do that, and then until they can't anymore, and that's how they find the minimal surface. It goes the other way around. You can think of it either way, okay? Okay, and here's Bekenstein-Hawking, just the case I started out with, where again the bottleneck just happens to be the horizon, and that's why the area is given by the horizon area. Okay, what does this have to do with what I said before about these puzzles? Well, first of all, you can prove that even when the bottleneck jumps, the thread configuration changes continuously. So it's just that the place that's giving the tightest obstruction has moved somewhere else, but the thread configuration itself changes continuously as you change A continuously, okay? Now let's go to quantities like mutual information and so on, and I'll do it through toy examples, and then I'll give some formulas or I'll flash some formulas quickly, but I want to illustrate the ideas. So you can show, so when we have 2 regions, then you may not be able to maximize the flux through both regions simultaneously. So you have a V of A, and you have a V of B, okay? But you can, and those in general will be distinct. But you can, in general, maximize the flux through nested regions. So you have A and A union B. You can show that you can simultaneously maximize the flux through both. So here's the set of V of A's, all the flows that maximize on A. Here's all the flows that maximize on AB. And there's a theorem that they overlap, that there exist flows that maximize on both, and I'll call that V of A comma B. Okay? So here's a simple example. So let's say S of A is 2 and S of B is 2, but S of AB is 3. The fact that the joint bottleneck is smaller than the sum, okay, so first of all, the mutual information is 1, the conditional entropy is 1. Now going to the geometry, the fact that the the joint bottleneck is smaller than the sum of these two means you can't have a V which simultaneously maximizes on A and B, because that would have a total flux of 4, which is not allowed in this example. So you maximize on A first, let's say. So you put 2 threads leaving A, and then you can only have 1 more thread leaving B, because the total number leaving A union B is 3, is at most 3. Or you do B first. So these are your 2 choices. And you see that we have a thread that can move back and forth. And we have a thread which is stuck on A, and we have a thread which is stuck on B. And you can show in general, not just in this simple example, that the number of threads you can move back and forth is equal to the mutual information. The number of threads that are stuck on A is the conditional entropy, and the number of A, and the number of threads that are stuck on B is the conditional mutual information, is the conditional entropy of B. Okay? So threads that are stuck on A, so the interpretation is that threads that are stuck on A represent bits that are unique to A. Threads that can move between A and B represent bits that are correlated, pairs of bits that are correlated between A and B. In other words, this thread represents a bit of A union B, which you can think of as living in A or in B. It's up to you because they're redundant. Okay, this example had a positive conditional entropy, but it's more fun if you have a negative one, because then you know there was entanglement. There was no entanglement in this example, there was just correlation. So let's constrict the joint bottleneck more to make S of A union B 1. Now the conditional entropy is negative, which means there must be entanglement. That can't happen classically. Now we have 2 threads leaving A. One of them can leave A union B. Where does the other one go? It has to go to B because it can't leave A union B. So that means we now must, by virtue of having a negative conditional entropy, we must have a thread which goes from A to B. Or if we maximize B first, then it goes from B to A. So we have 1 thread which moves back and forth like we did before, and we have 1 thread that connects A to B, okay, and that contributes 2 to the mutual information. So my claim is that a thread that connects A to B represents an entangled pair of bits, as opposed to a thread which moves back and forth but leaves A union B, which represents a classically correlated pair of bits. Okay? So we have our 2 lessons, what these threads mean, what the movement of these threads mean. And let's apply them, let's go back to this gauge freedom, the floppiness of the threads. Consider a single region, and as I said before, we have all this freedom to move the endpoint where the thread is attached to A. And we have this freedom to add these threads that begin and end on A, okay? If you now just divide A into 2 parts, and then apply lessons 1 and 2, we see that the freedom to move threads around on A, move where a thread attaches on A, reflects the fact that there's a lot of correlation between the different points of A. So do I have 5 minutes, or that's it? Okay. On the other hand, the freedom to add threads that begin and end on A reflects the fact that there's a lot of entanglement within A. So both of those are very physical facts about the state of A, okay? All of this can be done in equations, but I think I'm going to skip this. There's a very nice way to write the conditional entropy. There's a very nice way to write the mutual information. You can write the mutual information in a completely regulator-free manner. So you never have to, if you work in terms of flows instead of minimal surfaces, you never have to introduce a regulator to compute finite quantities like the mutual information. And the conditional mutual information is the amount of flux you can show, and this is what these equations mean. I'm not going to go through them. It's the amount of flux you can move between A and B if you maximize the number leaving C. So this is like conditioning on C, saying I demand to know the state of C, and now given that, how much correlation is there remaining between A and B? And that statement, that way of saying it, already proves strong subadditivity, okay? It already proves that that has to be a positive number. Okay, so I think what we've gained from this picture is a clearer connection between the calculation and the information-theoretic meaning of the quantities. Okay, that was the goal here. Okay, now one property whose information-theoretic meaning remains obscure, but which we can prove using the minimal surfaces, is this monogamy of mutual information inequality. Forget the name is terrible, but this is what the inequality is. It's sort of a stronger version of strong subadditivity. Strong subadditivity would just be saying this is larger than or equal to this term, but now it's saying even if you add this term, it's still greater than or equal to. This is not a general property of quantum states, but it is a general property of holographic states. But we don't really understand why or what it's telling us about holographic states. And I don't have a proof of this using flows, but I think it would be useful. How much time do I have left? Any? 0. Okay, so in my 0 time left, I'll just flash 3 extensions, getting the metric from thread configurations instead of the other way around, quantum corrections, and covariant version of the thread picture. Thank you.
Sunil?
Yeah. This picture is very suggestive. So I was just wondering if you have an asymptotically flat black hole, where you don't have a very clear principle of holography, can one think of bit threads going out from the black hole horizon to infinity, and somehow that smells a bit like the soft hair or soft BMS hair at infinity. So just wondering if that could be an explanation. So in a black hole, does the black hole have threads going out from it regardless of?
Yeah, I think so. I think so. Of course, so I mean, you could apply max flow min cut to that space-time and you would get and apply Ryu-Takayanagi and you would get the right answer. Of course, what we don't have is things other than black holes. So regions of the boundary, at least not yet, we don't understand that. But I think if this picture is correct, I would want to say that it's not just for ADS-CFT, it's for quantum gravity more generally. And then yes, you know, any black hole would have threads coming out of it. At least any
going to infinity.
And they would have to go to infinity.
Because they're divergenceless, so they have to.
Yeah, that would be for eternal black holes. Black holes from collapse, I would need to tell you this too.
Andy.
I want to make both a comment and a question. The comment is, in asymptotically flat space, there is a boundary, it's null infinity, and you can divide that boundary into pieces, and you can compute the quantum entanglement across this. It's a very interesting and subtle problem, which we've written a paper on recently, far from having solved it. But maybe this is relevant. But then my question is, what are the threads?
So I don't think that they are objects. I don't think that they, I think they're more like, I mean, I think they're more like the fabric of space. I mean, I don't think they're things in space. I don't think they're not like particles or strings or brains. So basically, you know, I think maybe one way to think about it is that we know that the geometry, if you're given the geometry and you have Ryu-Takayanagi, you know that the geometry encodes all of this information about all the entanglement entropies. And I think the threads are somehow the way that it does that. So it's the way that so a geometry kind of is a way of representing a quantum state. And somehow, you know, the threads are kind of some intermediate step between the quantum state just abstractly, which has all of its entanglement entropies, and this smooth classical geometry.
So could we have weird quantum states of threads that don't have a space-time interpretation?
Yeah, I mean, I think if you're not in the large N limit, if you're, you know, or you have some non-holographic state, you would have some crazy threads that don't kind of live in some, or don't kind of create some nice smooth geometry.
But then we need some kind of gauge symmetry because it's a redundant description. There's too many threads.
Yeah. So, I mean, I don't know. I mean, of course, I don't know the answer to your question. But maybe two baby steps. One is the quantum corrections, which I think I more or less understand. So, but this is of course just, you know, one over, you know, for leading order, the leading quantum corrections, and they're essentially you let the threads ignore the geometry to some small extent by jumping from point to point in the geometry, reflecting the entanglement of the bulk fields. And the time-dependent thing, and I'm not going to go through this, but it's maybe a clue, is that the threads remain one-dimensional. They don't. I mean, one confusing thing for us at first is do the threads gain a time direction and become world sheets? And it turns out that no. The right answer is that they remain one-dimensional. So they're sort of instantonic, and that again is saying you shouldn't think of them as objects.
Okay, I suggest we thank Matt Headrick again.